And you can see the screen okay?
Yes, yes.
Okay, good. Okay, I will start. I can figure this out. Okay. Okay, I think I will go ahead and start, if that's okay. I should have changed my picture because in Schenectady, where I live, at my house, we got about 20 centimeters of snow yesterday. So maybe I will show it on Friday. It will melt. It doesn't normally snow in April, but sometimes it does, and 20 centimeters is a lot. So yes, we call it a freak snowstorm. So, okay. So today I'm going to finish up on the properties and characterization methods for aerogels, and then the remaining talks will be about applications related to using aerogels. So, so far we've talked about microstructural properties, imaging methods, mechanical properties, some of the spectroscopic properties, and today I'm going to talk about thermal properties, primarily thermal conductivity, and just a little bit on specific heat. And then I will also talk a little bit about flow through aerogels, and a little bit about how gases permeate into aerogel materials. Okay, so I should have got this ready. Okay, so first of all, do you have an Easter bunny in Italy? Yeah, okay, so there's an Easter bunny on an aerogel with a blowtorch, and then I thought I would just show you, we'll see if this works. I may have to. There's
made out of chocolate.
yes, it is a chocolate bunny, yep. So, okay, now let's see if I can get this YouTube to work. I have a video of, let's see, of them using a blowtorch. Gel with chocolate on top. So we'll see if we can show it. I have to share. Okay, good. Looks like it'll work. Let me share the screen, right? Let's go back here. Nope, I don't need to raise my hand. Back. Share. Okay. Can you see the YouTube? Do you see the screen that says super insulation?
No, no, no.
Okay, hold on. Let me get it. All right.
Yes.
I didn't do it right. Let me try that again. Oh, because I didn't pick it. That's why. All right.
Can you share a desktop?
To share desktop. Which one is
Yeah.
this one? No.
Yes, you
Yeah.
can share-
Okay.
you share everything.
Yeah, that's good. Okay.
No, skip. Salta la prova.
Thank you. I know what they say in English. They're in the same place, but I'm not certain. Okay. This is a video of below. It's a fun video demonstrating how insulating aerogel is. So this is the American version of chocolate, Hershey's Kiss. Yes, not as good as Peruvian chocolate, but I think there's sound in here, but I don't think they're saying anything that great. And so they're just heating it up. That's been 3 minutes with that thing sitting on there. Chocolate looks like it's getting a little, maybe. Now it's 5 minutes. Still touch it. 7. If you look closely under the chocolate, you can see how it's getting white. I think it's getting wet, I think. It's water. Yeah, moisture. And the moisture will destroy the aerogel if it's not a hydrophobic one. So 20 minutes and it's still there, but it will melt because the moisture from the chocolate will harm the aerogel. Yeah, and so now it's not protected so much. It actually is a good demonstration. I talk about it, I think, on Friday about why it's good to have hydrophobic aerogels. So 25 minutes in. So now they burn it. Okay, I'm going to show it burned through. Yep. That's from buyaerogel.com. They sell aerogel samples, but I thought that was kind of that was to demonstrate. All right, now let me go back and see the right one. Okay, that was just a demonstration of everybody shows pictures of chocolate or flowers or something on top of an aerogel and it being protected. But of course, the aerogel will eventually, two things about that aerogel, it did get damaged because of the moisture. And so that's why it can be important in certain applications to chemically treat some of the things that Mary Carroll talked about to prepare the aerogel so that it can repel that water moisture and not damage it. So one of the things about aerogels, what makes them so interesting is that they are so thermally insulating. And so I'm going to talk a little bit about heat transfer in aerogels, the different mechanisms, what it is that makes them so insulating. And I'll talk a bit about how we measure the properties of aerogels, the thermal properties of aerogels, to see that. And I'll talk a bit about how you can make aerogels to minimize heat transfer or minimize the thermal conductivity. So there's 3 modes for heat transfer, and all 3 occur in an aerogel. Some are more prominent than others. So the first phase is conduction. That is the transfer of heat through the solid phase. Conduction occurs due to lattice vibrations in a material and due to the motion of electrons if it is a metal. Yeah. So it's affected by the backbone structure and the way the structures are connected, and it's affected by the chemical composition. Depends on what it's made of. You know, is it a silica, alumina? What kind of aerogel is it? And it is limited by extremely small connections between particles making up that conduction path. So here's an image. This is from the aerogel handbook. Again, here are those colloidal particles of silica, the little sphere things we like to draw when we talk about aerogels. And so the red is indicating kind of a path for conduction. It would travel through, it's obviously going to travel in all directions, but it will travel through the solid material. So heat can travel through the solid material via conduction, right? And you obviously have to have the temperature difference across that to have it happen. The second phase or a manner for heat transfer is convection, which we call the fluid phase. So you transfer heat because the gas can move, and with it, it can transfer heat. And with the aerogel, it's very dependent on the pore structure. And so the pores, and I'll talk more about this, you have what's called the Knudsen effect, which has to do with the fact that the pores are on the order of the mean free path, or can be smaller, of the mean free path of the gas molecules. And so I'll talk about that. So that's very important when we talk about convection and aerogels. So it can result in that part of the thermal conductivity could be, if you have it filled with air, it could be less than that of air. So the molecules can tend to collide with the solid network maybe as frequently as they collide with each other. And so this is the blue kind of showing you convection, what's happening in there. And again, I'll talk a little more about that mechanism in a few more slides. And then radiation can occur within the aerogel, and that will depend on the optical thickness and type of aerogel. It tends to be low because they have low mass fractions, but it does increase with temperature. So it's not a concern, not much of a concern at moderate temperatures, but if you have an aerogel at a high temperature environment, it is more important. And the radiation is sort of shown by the yellow things. You don't have to have any medium for radiation to occur. And all of these occur because you might have a temperature difference across your material. Okay, so let's talk a little more about conduction in the solid. So conduction gets inhibited because there's contact resistance between the primary particles. So if I look at two particles, these colloidal particles, and again, I'm always using the example of silica because that's what I do a lot of work with, but it can be made of many different materials. But as these primary particles, where they join, right, there's a neck there. It's smaller, and that creates a contact resistance. And, you know, we talked about earlier, aging changes some of that, it might lessen that. So aging will have an impact on the structure and could impact the thermal conduction that happens. The other thing that happens is that not only do you have this resistance, but we have dead ends, right? We may just kind of be going along here and then this just stops. You know, there are many dead ends in a aerogel structure. So that also inhibits conduction. It's affected by the composition. How is it made up? In an example, dense silica, think of as a single pane window, a glass. The solid conduction is relatively high. So thermal conductivity through something like glass might be as high as, I don't know, 2 to 3 watts per meter squared Kelvin, watts per meter Kelvin. Whereas silica aerogel possesses a very small amount of solid silica, you know, 1 to maybe 10% of it in there. So that thermal conductivity is much, much lower. So it's, again, how is the material configured, and in what format it is. So Again, silica itself, if it's dense, has a much higher conductivity relative to, say, a silica aerogel. And that has to do with the way that the aerogel is made up. Yes.
I didn't fully understand what does it mean that there is contact resistance between primary parts.
Okay.
Primary particles such as protons and electrons.
No, as in between these, so envision this is a bunch of silica,
Okay.
like this. So the way they're connected, it's not a cylinder, right, where the path would be straight through. What happens as the heat flows through, it gets constricted through that. So my primary particles I made of like the silica.
Okay.
Yeah. So that resistance, again, where the area decreases, and let's say you have heat flowing in this direction, this will inhibit it versus if it was just a cylinder, you'd have more. Yeah. Yes, the contact points creates it. Yes. Yes. Any questions from online?
No.
Okay. So there's not a lot that can be done to minimize that part of the overall thermal transport in an aerogel. Don't forget, there's the three parts: conduction, convection, and radiations. And I'm just talking about conduction. So there is not that much that can be done to reduce thermal transport through the solid silica, or the solid structure again, of any aerogel. I'm talking about silica. So we could do lower density aerogels, and people have prepared very low density aerogels, which reduces the amount of solid material, which would reduce the conduction through the solid material. But this tends to lead to aerogels that are just weaker. And then the other problem is that as you reduce the amount of solid material, the mean pore diameter is going to increase. So if you have less solid material, you've got more air gaps, and that could increase the gaseous component of conductivity. So it's a bit of a trade-off. So there's not a whole lot. I mean, again, you can change for an aerogel in general, you can use different materials may affect that. But once you have, say, silica, there's not a lot you can do about that part of that phase of or type of heat transfer through the material. So moving on to the second mode of heat transfer, which is convection. And so, you know, the characteristics we saw from the pore distributions, that the characteristic pore size within aerogels is typically somewhere in the 10 to 100 nanometer range. And again, that depends on the type of aerogel. For silica, it's, you know, somewhere in there. And so when you have the gaseous phase in the aerogel structure, it's reduced compared to if you just had the free gas. And that, again, has to do with the size of the pores in the aerogel structure. So heat transfer in the gaseous phase is characterized by the Knudsen number. We will see this when we talk about gas flow through the materials also, because the Knudsen number comes in there. So the Knudsen number, Kn, is the ratio of the mean free path, L sub G, of the gas molecules, and the effective pore dimension, D. So the mean free path of a gas molecule is sort of the distance it will travel before hitting something. And so we can talk about two types of heat transfer. In one case, if the Knudsen number, so if the mean free path of a molecule compared to the diameter is much larger than the diameter, a molecule is likely, and that's sort of shown in with these open symbols, it's likely to hit the wall. So this, the gray would indicate sort of the wall of a channel, And here's the open space, sort of the pores. So in that case, a molecule is more likely to hit a wall than it is another molecule. So transport of heat under that phase involves the gas hitting the solid and that sort of interaction. If the mean free path is smaller than the diameter, and those particles are more likely to hit another particle, and that's shown with these dark particles. And so transport of energy would be via classical diffusion of gases, you'll see. So we can talk more about each of those regions. So Knudsen number greater than 1 means the average pore size, the diameter, is significantly smaller than the mean free path of the gas molecules. Okay, so that is this case. So those gas molecules are likely to just hit the wall. So they collide predominantly with the solid backbone of the aerogel. And then the resulting, what you could call thermal conductivity contribution from the gas phase is proportional to the number of gas molecules. So the more gas molecules you have in there, the more they're interacting with the solid and the more they're transferring energy. And so that's directly related to gas pressure. If instead the average pore size is much larger than the mean free path of the gas molecules, right, which results in this is very large, Knudsen number is small, we have this kind of energy transport with the molecules. So they predominantly collide with each other, which is the classic case of conduction heat transfer. The resulting thermal conductivity of that component equals the thermal conductivity of the free gas. So it would be the if it's air, it's going to be the thermal conductivity of the air. And that's independent of the gas pressure for ambient and moderate pressures. And what we're also assuming, I talk about convection, which has to do with the motion, the motion of the gas phase in the porous structure. And in fact, we don't have a lot of motion, that kind of phase is suppressed. So we really sort of think about it being conduction in the gas if it's not moving. Okay, so it's, again, it's either molecular or diffusion is the conduction, normal diffusion that you would see. And then, of course, it can be in the transition regime. Recall, aerogels have a range of pore sizes. So in some cases, you may be seeing molecular heat transfer where the gas molecules are hitting the solid and you have that interaction. And in other pores, you might see conduction heat transfer. So that's sort of a transition regime where the Knudsen number is near 1. And again, it's related to the diameter of the pores, and we know there is a range of pore sizes in an aerogel, but the predominant ones are pretty small, and they're going to put any aerogel, many of the pores will be in this regime, molecular heat transfer. So, yes, okay. Okay. So it's also complicated by the contribution of the gas phase within the aerogel is complicated by the fact that heat transfer in the solid backbone interacts with that in the gaseous phase. And so that depends on the structure of the aerogel and the gas phase. So this is a nice schematic from the aerogel handbook. So this sort of shows what's going on. So we can talk about an evacuated aerogel, an aerogel at a low gas pressure and an aerogel at a high gas pressure. And so on the left here, we see the whole thing is showing this coupling effect between the solid phase, which is shown in these red arrows, and then what's happening with the gas molecules shown in green. So if your structure is evacuated completely, there is no interaction of the gaseous phase with the solid phase. This contact, I call it, in heat transfer, we call it a contact resistance between two surfaces. You can think of each of these silica spheres as different surfaces, and where they touch, we have this contact resistance, and it's relatively high in an evacuated space. But now, if I increase the gas pressure, I'm going to get gas molecules in here that are going to interact between these surfaces, right? They tend to hit the surfaces. And so that is going to change my contact resistance, because not only can I transfer heat via conduction in the solid from particle to particle, I can also have heat be transferred due to the gas itself interacting with the solid. And then as you go to higher gas pressures, you just get more of the gas material in there interacting more with the case. So you end up, transferring. This sort of would have the lowest overall thermal conductivity. Again, thermal conductivity is a property of a material that says how much thermal energy is being transferred through it. So we have this interaction. So this would have low thermal conductivity, and this is tending to have a higher thermal conductivity due to the interaction of the gas with the solid phase. So you can show this. So this is a plot. This is a resorcinol formaldehyde aerogel, relatively higher density, 0.3 grams per milliliter, about 80% porosity. And these are larger materials. Their average pore size is like 600 nanometers, much bigger. But what they did is they made some measurements of the thermal conductivity over a range of pressures, and this was done in argon. And so you can see higher, so this is ambient. As you increase pressure, the thermal conductivity goes up, which is agreeing with this type of idea, okay, that you just have more gas molecules interacting in that. And then as you evacuate it, which is approaching this kind of situation, the thermal conductivity drops immensely. So it's five-fold change, 5 times change in that value over this pressure range, which is large. This is a model. There are some Knudsen models for heat transfer. And if you ignore the coupling and you just do the Knudsen model, you get something like this. So it ignores the coupling and doesn't predict that. But so what I'm trying to show here is just that interaction of the gaseous phase with the solid phase and how that affects the heat transport in an aerogel. Questions?
Not yet. I have to.
Okay.
I have to listen a little bit more.
Okay. Okay. Is my speed okay?
Yeah.
Okay.
Thank you.
Okay. So how can we minimize this phase, this contribution to the overall transport properties? So the idea is that we want to increase the mean free path relative to the mean pore diameter. So we can do this in different ways. You could fill the gas with a lower molecular mass. Fill the aerogel with a gas with a lower molecular mass, which will have a longer mean free path than air. But it's not necessarily easy to do that. They tend to be more expensive, and they could escape the system. You can try to reduce the pore diameter by increasing the density of the aerogel, but that would increase the solid conductivity component. So both of those are somewhat problematic. You can, depending on using different chemical preparation methods, you can change the pore diameter a little bit while keeping the density constant. And for example, you can achieve that using either the tetramethyl orthosilicate, the TMOS, versus the tetraethyl orthosilicate, which leads to smaller diameters and similar densities. So that could help. The easiest, not the easiest thing, but one of the most effective ways to lower the gas pressure in an aerogel is to lower the gas pressure or evacuate. There are a lot of vacuum insulation things used. And in an aerogel, it's necessary only to reduce the pressure. You don't need a very, very low vacuum. You need a moderate vacuum. So at about 7 kilopascals gives you pretty good performance. And I have a plot also of that. So this plots thermal conductivity. This is effective versus gas pressure, similar to the other one, but here just showing some different aerogels. I also want to say that I use the symbol K for the property thermal conductivity. But also people use lambda, the Greek symbol lambda, to represent thermal conductivity. And I have not figured out if that is US versus Europe, or I think it's engineering versus physicists is what I think. I think physicists use lambda. So anyway, so sometimes you'll see plots with lambda, sometimes you'll see, I'll refer to K, they're the same thing, they're the thermal conductivity. But this is a plot showing thermal conductivity of a carbon aerogel, phenolic peripheral aerogel, I don't really know what that is, and a silica aerogel. And here you can just see that great reduction in thermal conductivity. And I believe this is in a nitrogen environment. And you've got thermal conductivities below that of the nitrogen itself, which is about up here. So this is done, and I'm going to show you some more examples of differences. There's also a big difference between aerogel monoliths versus aerogel granules in this. I may have that come up soon. But this is done typically, this can be done in window applications when you make an aerogel. If you evacuate it, you'll get even better performance. Yeah, here it is. So the other interesting thing is we talked about you can have aerogels in granular form or the monolithic form. And so this was the study that showed the thermal conductivity, again, versus pressure for aerogel granules in blue and a monolithic aerogel in red. And so you get, when you reduce that pressure, the thermal conductivities of both materials decreases. But the thermal conductivity of the monolithic form of the aerogel decreases even more. So this was something, and I'll talk about this more on Friday because the work I do has to do with monoliths and particularly in window applications. And so we were showing that not only do monoliths give you better visibility, if you use a vacuum or you evacuate your system, you get even better thermal performance. You know, but at atmospheric pressure, they're the same. That's not really any difference, but it's when you pull a vacuum. And this plot over here just shows, and this was for a sort of a window application. And this is the thermal resistance value of aerogels. and my apologies because I have used terrible English units here that I don't even understand. But what matters is the difference in the value. So having a higher resistance is better if you're trying to insulate something. So this was a case where you have the granules in the aerogels at atmospheric pressure, and for an inch thick monolith and an inch thick of granular, both will provide the same thermal insulating value. But if you have a small vacuum, which is this amount, you can see that your monoliths give you, not quite double, but close to double the thermal insulating value. So it's a interesting thing that you see with the aerogels versus granules. But all this is, again, goes back to the what we saw with the difference between the molecular diffusion and the conduction that goes on. Okay, the third mode of heat yes.
A couple of questions.
Yes.
So just for the last slide.
Yes.
It may be being said that granular and monolithic aerogel have the same what's the name, thermal conductivity at atmospheric pressure, because both of them are made out of 98% of air.
Yes. Yes.
For this reason.
Yes. Yep. But then when you evacuate the monolith, I believe the issue with the granular, the little granule has that, but you also have air between the pieces of granule. I think that affects what's going on. Okay, you had another question?
Yes, I have another question on nuts and number.
Yes.
Maybe. So we have said that if you have a nuts and number higher or lower than 1,
yes,
then something change about your
yes,
hydrogen.
Yes.
And what is the preferred condition you should have on nuts and numbers? So higher than 1, around 1, lower than 1, because it's something like how the heat is transferred.
Yeah. Yes.
Right?
Yes. So if you have, you can suppress it. Generally, you are in this regime here with the molecular heat transfer. And if you want to, let me talk about it here. So if we want to minimize, well, so it depends. There's conduction, there's convection, what's going on in there. So if you want to minimize the conduction, you want to increase the mean free path of something. Sorry, I said convection. So if I increase this, I'm more in this molecular heat transfer range. It's going to be, so if your Knudsen number is very small, you're in what's called a continuum range. And so then you will have the properties of the gas, like the thermal conductivity of the air. But if it is in the molecular region, that will be suppressed. It will be lower. You'll get a lower conductivity. But it's complicated because there's also the solid phase too.
So the Knudsen number is what? Okay, now I have it in Italian, but okay. So the Knudsen number is what made the difference between air and hydrogen.
Sort of, yes.
So if you have a Knudsen number lower than 1, it's a sort of your hydrogen is like air.
Yes. What for the purposes
of convection.
Yes, of convection. Yes, for the purpose. If it's like a channel, it doesn't have all these small pores.
Like
yes,
hole.
Yes, exactly. That's exactly what's happening.
Okay.
Other question?
No, I think
Okay, good. I like questions. Okay, radiation. So the amount of radiation that you're going to have will depend on the optical thickness of a specific type of aerogel, or the optical depth, which has to do with how sort of the extinction coefficient of a material. I'm not an expert on radiation. I don't worry too much about it because that work at lower temperatures. So for most optically thick aerosols, these are organic, opacified carbon aerosols, the radiation is not particularly important. However, in a silica aerogel, which we like for their visible transparency, so that you can use them in windows or skylights, the problem is they are quite transparent in the infrared region. So there is radiation. But at low temperatures, it's not particularly important. But at higher temperatures, it is important and you have to deal with it. And so I have a example. So this is an example of a study done by Pam Norris. Actually, I don't know if she did the study, but she's published it at University of Virginia. So as temperature increases, the radiative component becomes more important. And it's kind of, if you're talking about something above, say, 200 degrees C, and you're going to have to suppress it if you're trying to minimize, if you're using silica aerogel as an insulator. And the way this can be accomplished is to add an additional component to the aerogel, either before or after supercritical drying. Usually it's done before, but you want to do this without interfering with the mechanical integrity of the aerogel. It won't do any good. So one additive, and this is an example of an additive, is carbon black, or elemental carbon. It's an effective absorber of infrared radiation and also can increase the strength of an aerogel. So this just shows an example of a pure silica aerogel. And I don't know what temperature, I think this is at higher temperature. This is thermal conductivity again versus pressure. But you can see in blue, it approaches sort of 8 milliwatts per meter K. But if you are able to dope it, put some carbon black in there, you can reduce that significantly. And that reduction is primarily due to the radiation is reduced on that. So this here would be ambient, and then again under pressure. So that's how what people do with radiation. But again, the carbon, it's not going to be transparent. So unfortunately, in applications where you want them transparent, for windows, hopefully it's not 200 degrees C, although for high temperature furnaces, you would have that problem. Okay, so just to summarize thermal conductivity, so it can be represented as the sum of the contributions from conduction through the solid, conduction through the gas, and radiation through the particles and voids. And so this plot shows total thermal conductivity is here versus, so this is versus density. So total thermal conductivity versus density. You have the gaseous phase, which is shown here. So as a material gets more dense, the gaseous conductivity decreases because there's more solid in it. Oops. Yeah, yes, get back there. Okay. The solid conductivity, which is this line, and with the triangles, increases with density, which makes more sense. You have more material, so it goes through. And then the radiative conductivity is shown to decrease. But the net looks something like this. And this is a resorcinol formaldehyde aerogel, just showing what happens with density. But what happens with density is, will be true of the other types of materials. So those are the things that contribute to thermal conductivity. Again, thermal conductivity is something we try to minimize if we're using these as an insulating material. So I'm going to switch gears a little bit and talk about how to measure thermal conductivity. And this will probably take me about 10 more minutes, and then we'll take a break and I'll switch to talking about gas flow and aerogels. So it's very difficult to experimentally measure the thermal conductivity of an aerogel because an aerogel is very low thermal conductivity. It's very insulating. There's two types of methods. There's either steady state methods, which involve guarded hot plates or heat flow meters, and I'll explain those in a minute. It's something shown here. And there's all kinds of standards for using steady state. Or there are transient methods, which tend to heat something. The steady state, you heat something up for a long time and you can measure temperatures to get data. Transient, you heat something and you measure the temperature response. There's the hot wire, the laser flash, and the hot disk method. This is the hot disk method. We'll talk briefly about all of those. And the thing to consider when you are choosing something is what size sample do you need? How much of your sample do you need? What geometry do you need? Is it isotropic material? And then how much time do you have for an experiment? So the steady state method is very accurate if you can do it. The elements are, so the first, the guarded hot plate, you have a heater, a plate in here that is heated. You put your sample on either side of that plate, and then you have a cooling or a heat sink plate in blue on the outside. That's the two sample method. The one sample method, that people call it a heat flow meter, would be you have a hot plate, one sample of your material, and a cooling plate on the other side. In either case, you have to, so the one sample method, one of the complications, you have to insulate it because you want to have all of the heat coming from your hot plate to go through your material. And what's hard about aerogels is they are so insulated. So how do you insulate with something more insulating than an aerogel? The other thing with a guarded hot plate, what you have to do, and what's nice about this is it's a symmetric system. You don't have to insulate it around so much, but you have to have what's called guard heaters. So if this thing is heated, you want to maintain one-dimensional heat flow, in the sort of Y direction. I don't want heat flow going out in the X direction out here. So you also need to have some kind of guard heater to maintain temperatures there. So it's important you have to have samples with a well-defined thickness. They need to be flat. Put it in there. And the technique is that the sample plate is placed between the two, for the two-plate method. And the power to the heating plate is regulated so that the temperature difference across the sample from the bottom to the sample to the top of the sample is constant. Again, that we provide a guard heater at the edge, so all of the energy produced here flows through. It's an energy balance. And at steady state, you can calculate the thermal conductivity, K or lambda, whichever symbol you prefer, is going to be equal to, this is from Fourier's law of heat conduction, assuming all of the power that goes into that plate is conducted through, times the thickness of the sample, divided by the sample area, divided by the temperature difference you measure across there. And so this is a pretty, it's a very established method for measuring thermal conductivity. It's accurate if you design your system right, or using, there's many systems out there, test labs do this. This problem with this is you generally need large samples. These need to be, I mean, there are some smaller samples, but we're talking 15 to 30 centimeters. They need to be big. They need to be flat. And for this, you need two samples. And the other drawback is this takes a long time. So the test is not short time. It can take a long time to run this test. So some people prefer these transient methods. And there's one called a hot wire method. And the technique is that you use a thin flat, so your sample is here in gray, and you embed in your sample a platinum wire, which has a known temperature resistance relation. So the resistance of that wire can be measured, and it's a function of temperature. So you can either prepare your wire and put your sample around it, or I like this from this work that they did at MIT. They actually made their aerogel. They embedded a hot wire right into the aerogel when they did the sol gel processing. So they made it in there. So I thought that was clever. They did that. So the way you then, what you do is you heat the wire with a constant electrical power. The wire serves as a temperature sensor and also as the source of this energy that gets dissipated into the material. So the temperature increase of the sensor is calculated from the electrical resistance. So you measure the electrical resistance of the wire with time and correlate that to temperature. And that temperature rise, and this is a typical plot of a hot wire temperature rise versus time. So on the vertical axis is temperature rise. On the horizontal it's a log of time. So look something like this. You have some stuff going on with the wire, and then you have a linear, on a log plot region for your temperature rise. And so that temperature rise rate is related to the material that your wire is embedded in. And so the thermal conductivity is evaluated by looking at this behavior of temperature versus time. So depending on the heat flux per unit length from the wire, the temperature of the wire and the time, you can convert you can calculate thermal conductivity. Nice thing about this is it's fast. These tests do not take a particularly long time, on the order of minutes. But there are issues also with this in terms of end effects and things like that and getting accurate results. But it is a fast method. And the sample does not need to be particularly large. The sample's on the order of centimeters, not a few centimeters. Another similar method is the laser flash method. And it's kind of like that. You have a sample and you flash it on one side with a short laser pulse. And on the other side, you detect the temperature. So the heat diffuses through the sample and results in a temperature rise on the rear of the sample that's monitored with an IR detector. And the change of the rear temperature with time is fitted. And there's a differential equation and the boundary conditions that you can solve for that. And it allows you to calculate, what it actually calculates is the thermal diffusivity, which is the ratio of the thermal conductivity to the thermal capacity of a material. So alpha, we use symbol alpha. And it signifies the ability of a substance to conduct heat relative to its ability to store heat. So that's what you actually measure. If you know the density and the specific heat of your sample, you can then calculate your thermal conductivity. So alpha is the thermal diffusivity, which is what you measure using this technique. And if you know the density and the specific heat, you can then get thermal conductivity. And again, this is one of those shorter techniques for getting data. And then the last of the methods I'll talk about is this thing called the hot disk method. And this is what we use at Union College. You have a sensor that is shown here in this orange color. And in fact, the sensor is orange because it's made from Kapton. And the sensor has wires embedded in it. And so you take a sensor and you place it between two identical samples. So again, for this technique, you need two samples. You energize the sensor, and the temperature is monitored over time. So it's similar in a lot of ways to the hot wire, in that your sensor heats and records the temperature. And so your thermal conductivity is related, again, to the time rate of change of the temperature that is measured. And so you can use that. So as this sensor is heated, the energy penetrates into your samples. And so just like the other sort of transient techniques, same thing, the thermal conductivity is related to the things that are around it, with the material around it. It is a nice technique because it is very fast. The tests take about, takes like 5 minutes to set up, and it takes like 1 minute to run a test, which is very nice. You also only need small samples. Your sample size is dictated by the size of your sensor, so you can get down to a few centimeters diameter sample. It does require 2 identical samples, so that complicates things. And there are some issues with this technique with the very low thermal conductivity materials, and porous materials like an aerogel. And there's a very good paper out recently that has a correction factor for that. So for example, we use this to measure thermal conductivity of our aerogels. And we typically measure for silica aerogels about 30 to 35 milliwatts per meter Kelvin. If I make a large sample of aerogel and send it used to an organization that does the guarded plate method, we know our samples are more like 20 milliwatts per meter Kelvin. So I'm currently investigating more on this to see what I can correct the data. But it's nice for us, it's nice for comparison techniques. So we do that to compare things. It's also very nice because you can measure thermal conductivity over a huge range of thermal conductivities with this technique. So anyways, there's either steady state or transient techniques. Time is a factor, size of your sample is a factor. None of them are particular, these hot disk method is not inexpensive, nor is this. I think this one probably you can build your own. But the big thing also is just it's hard to measure thermal conductivity of such low thermal conductivity materials. And there's some very specialized equipments at some of the national labs for doing that. Okay, I just have 2 slides and then we'll take a break. I just want to finish up on thermal properties. So the only other thing is the specific heat of aerogels, right? So specific heat is a measure of the amount of heat required to increase the temperature of a unit mass of a substance by 1 degrees Kelvin. And so it has to do with the capacity of a material to store heat. The higher the specific heat, the slower the heat propagation within the material, if the density is constant. I don't know what I have in my things here. Okay, so the only data I've really seen out there is from the aerogel handbook. This is specific heat. It's in joules per kilogram Kelvin, CP, versus temperature. It goes from 0.1 to 1,000 Kelvin. And there's some data for silica aerogel of different densities. The red are a little more dense aerogel, and the black are 2 different aerogels. I think this must be the lower density up here. And it kind of shows you the behavior of specific heat with temperature. For comparison, specific heat of glass at room temperature, which I guess would be somewhere over here. Oh, no problem. It's perfect. I just finished my coffee. Okay, we'll go ahead and get started again. Okay, so that was thermal conductivity, and the last kind of property, not really a property, sort of a property measure, I guess, diffusivity, but is looking at gas flow through aerogels. Gas doesn't really flow well through aerogels for many of the reasons I talked about with the thermal transport. But it's of interest, particularly in sort of sensing applications where you can use aerogel, you can dope an aerogel with something to respond to oxygen or something else. It's important for some of the work that we do on catalysis, trying to, for pollution mitigation and pollution cleanup operations. So I'll talk a little bit about it, and as some of the work we've done in the area, but it's in process, that work. But so the idea is that obviously porosity and pore size indicate how much empty space is in a sample and how it's broken up. And while it's true that materials that are more porous tend to allow more fluid to pass through, at least when we talk about macro porosity, right? Bigger the holes, the easier it is to flow something through it. But it's not hard to imagine a material made up of isolated and dead end pores, right, where the pores don't go anywhere. It could have a high porosity, but it might not allow any fluid flow through its structure. So when you think about aerogels, and other porous materials, it's important to consider how pores are connected to each other and the topology and how the voids and how they're connected. And so there's two things that you sort of need to consider when you're thinking about that, and they are connectivity and tortuosity. So connectivity is defined as the number of non-redundant, so non-repeating, closed loop paths which can be drawn through a network. So a higher connectivity per unit volume means the pores are just more connected. There's more likely to have a path through those pores. And while simple in definition, it's sort of difficult to measure. You can also talk about the connectivity of not only of the pores, but in this picture here is the aerogel structure again, and we talk about the connectivity of the structure. And so these are two sketches of the aerogel structure. And we have low connectivity and high conductivity. So low connectivity is shown here. We're talking about connectivity between the structure, and higher connectivity here. So if we look at points A and B on each one, and just the black line represents the straight distance between them. And then the blue line represents the minimum path to travel between those two. And so in this, we would say these pores, the solid material. I'm talking about the solid material connectivity, but the idea is the same. You can think of the pore connectivity is also of importance. But this is sort of illustrating it on the solid. But in these two cases, so this is low connectivity and higher connectivity because you have a more direct path. You could imagine this is as the pores, but this sort of shows also you have, it's called dead mass on this side. This doesn't go anywhere, right? These green things. And then in red, you have the neck regions, okay, between these things as shown here. So this has low connectivity because you have these things that don't go anywhere, so they're not connected in the red regions. Okay, so it's something that's difficult to measure. also, but think of, I'm showing you pictures of the solid, but also the same thing applies to the pores. How are they connected? Right, same idea. The other thing that's important is tortuosity. So the path of the flow through the material can be described using the tortuosity. So how bent is the path that you have to go through? And so a higher tortuosity increases level of deformation. So here's a picture. This is from a geological site. I like the picture. You know, if you have 2 points that are a distance L0 apart, but if you actually have to travel like this through it, and you can imagine in an aerogel structure, you have to travel kind of a tortuous path. They characterize the tortuosity as L over L0, the difference between those two. And this also, you see it in this structure. So both of those, both connectivity, and again, when I'm talking about flow through aerogels, I mean of the pores. How are they connected? Can your material flow through it, or is it just going to reach dead ends? And if so, when it's connected, what kind of path does it have to take to get through the aerogel? So those are things you have to consider when you're looking at an aerogel. And then this is just sort of, I'm going to talk about some experiments that people have done to measure flow through, and some of the ones we've done. So define some variables. And so phi, Greek symbol phi, is used to represent the flow rate, and we use it as an energy rate in watts. So that's the flow through a material. So imagine this is an aerogel sample, and I want to measure the flow through that sample. So I can, if I, nope, that, I missed one. That should be delta P next to that. But if I flow something through an aerogel of face area or cross-sectional area A, and thickness L, I can measure a pressure drop across it. And so from that, I can calculate something that is called a conductance, which is going to be equal to my flow rate divided by the pressure drop. And there are many different sort of names given for these, some of these, and many different symbols that I've seen in the aerogel literature. For now, I'll use D. And then the other thing we can get is the gas permeability, which, so this thing is in meters cubed per second. Gas permeability, or people also call it the diffusivity, how the gas diffuses into the material. And I'm going to use capital K. This is not thermal conductivity, this is diffusivity. It's just the conductance times the length divided by the area. And it's independent of size, so it's meters squared per second. So these are some of the properties that people measure when looking at flow through aerogels. How do you get flow through aerogels? So back to the Knudsen number, because again, the same thing that describes the method of the physics of the heat transfer, the energy transport also describes the flow transport. And so again, we have the Knudsen number, and I have this picture again, where we have the mean free path and the effective pore diameter. So this would be the effective pore diameter, you know, the height of this channel. This isn't really a pore, but it's a channel. And so if you classify flow regimes, sort of the very low Knudsen number is the continuum region, right? That just means that molecules are just going to flow through continuously, and you don't have to analyze the system in a more of a discrete region. So there's a continuum region and a molecular region. And this is sort of classical fluid mechanics assumes this, but we're really down more in this region. So again, and this is a little bit like what I showed with the convection when we were talking about heat transport. But so molecular diffusion, again, high Knudsen numbers. The average pore size is significantly smaller than the mean free path. Right, so this pore size, I should have given a thing. In this case, this is pore size. In this case, this is conductance. So I'll try to be clear with those. So In that case, right, the molecules predominantly collide with the solid backbone of the aerogel, and the force for that flow is concentration difference. And so the conductance there is related to basically the 1 over the square root of the molecular weight of the gas. So this is just the gas constant, depends on the temperature. It depends on the radius and the length. So the radius would be this dimension and the length would be that dimension. But the conductance is related to the molecular weight, and so it depends on different gases, how that's going to behave for a different aerogel. In the viscous flow or the continuum flow region with the small Knudsen numbers, again, the pore size is much larger than the mean free path, so the molecules hit each other. You know, they're more likely to hit each other than to hit the walls. And so flow is driven by a pressure gradient. So that's what drives. So in the other case, you have, you know, concentration difference. Here you have a pressure gradient that's driving the flow, and you have a viscosity that opposes the flow. And so classical fluid dynamics is Darcy's law, which gives us a conductance. And the conductance is related to, again, the pore, kind of the pore size, this dimension, the pore length, the average pressure, and then the viscosity of the gas. So that will depend on the gas property. So conductance varies with average pressure and inversely varies with the viscosity of the particular gas you're looking at. And so in the transition region, you sort of have both going on. So there are sort of two ways to measure conductance or diffusion. Again, they're related. One way is to place a sample. So this would be an aerogel in a chamber and seal it. And there's an opening on the bottom, and you evacuate this side, and then you flow gas through the top, and you measure the pressure from top to bottom. And so you meter the flow rate. You measure how much flow is going through, and you measure the pressure difference to learn about. Then you can calculate the conductance when you do that. This technique is difficult because you have to, I know, because we built something to do this, it's very hard to seal that sample with that. Another technique instead relies on this technique is also difficult because it's difficult to measure the low flow rates. A different technique relies on monitoring pressure changes. So you would have a sample of your aerogel in a tank over here. You evacuate it initially. You pressurize a pressure tank. You open the valve and you measure the pressure response as the gas flows into your sample. And so these are the two main methods that are in the literature for doing this, and they're somewhat little bit different. I mean, they're different techniques, but this is also clearly measuring sort of a steady state flow. You're forcing flow through a material, where this is not quite the same. So this work is from Hostica at University of Virginia. And so what they do is they measure in that system, they have their flow rate and they have their pressure drop across the sample. And so this was done at an average pressure. And you can take that information, and from that, you can determine what that conductance is. Okay, or you can determine the diffusivity across there, depending on how you plot that. And so you can measure the pressure drop versus flow rate and calculate the conductance from the slope, and it corresponds to a specific average pressure. So even though delta P is increasing, it's always staying around the average, same average. And you can do that for different average pressures. And then you can get conductance or gas permeability or diffusion coefficient, or you called many things for different cases. So you repeat it at multiple pressures. And you can plot the results. And so this is sort of showing what you get, gas permeability or conductance, however you want to plot them. People use both, versus P average. And if your behavior looks like this, plot, that's diffusive or the molecular flow, because again, going back here, it doesn't depend on the pressure. This one depends on the pressure. So if your behavior looks like this, you're in that viscous or continuum region. So you can study different materials by sort of that setup I just showed you and get this information and determine something about the nature of the flow. And so in fact, this is results from that study. So they measured the gas conductance at pressures ranging from 6 to 200 kPa with nitrogen and helium. And as you lower the gas pressure, you increase the mean free path. So this is they call this their conductance, but I think it's permeability, but it doesn't really matter because samples are all the same size. So this is it's called conductance versus pressure, right? And so as you lower the pressure, and up on the top, they've plotted the mean free path of the material, whether it's in helium, and here this gamma is mean free path, helium or nitrogen. Okay, so this is increasing your Knudsen number, approaching molecular diffusion as you go lower and lower. So the particular sample was a pretty low density aerogel, surface area of 800 and a mesopore diameter average of 24 newtons. Okay, nanometers, sorry. But there are pores. The instrument measures pores from 2 to 200 nanometers, and there are also, when you use gas absorption, it doesn't tell you macropores. So what they found, so they plot diffusion coefficient versus P, and again, going back here, if it's horizontal or increasing with P tells you something about the flow. And so they found this sort of thing, and they didn't see a clear cutoff. So this would sort of indicate your viscous flow region. Okay, you're getting down to lower Knudsen numbers. They don't really see the horizontal behavior as much, maybe a little bit here. So the other thing they did is they were able to plot the ratio. So the ratio of the conductance of the two gases, if it's purely viscous flow, that ratio, again, the R, the L, the P average are all the same, is going to be the ratio of the viscosities of the gases. So the viscosity of helium and the viscosity of nitrogen. Or if it's purely this molecular diffusion flow, it's going to be related to the square root of the molecular mass of the two gases. So they sort of cleverly plotted this ratio, and here's what it would be for pure diffusive, the molecular flow. It would be that, and here's what it would be for purely viscous flow. And so what they're saying is they really are in a regime under these conditions where you have more of a mixed flow. And they are attributing that to, which I think is a very good thing, there is a distribution of pore sizes. And so we really have to account for that. It's not one or the other. You sort of have both things going on. So that was one flow. There again, there are some issues with trying to measure flow through concealing those aerogels to get the flow through the aerogel, and it is also a case where they are forcing the flow through there. So the other technique is this pressure measurement method, and this is again based on some work by Stumpf et al. In Germany. And so we actually have a system at Union where we built one, and it looks like this. This is our pressure tank. Doesn't look like much of a tank. It's very small. Doesn't need to be very big. This is our aerogel chamber. Okay, and you can see schematically. So we put the aerogel in here. We evacuate it. Okay, so close off all the other valves, close that off, evacuate the system, and then pressurize our tank, and then open the valve between the two and measure the pressure in the aerogel chamber as you pressurize, as you flow into it. And it's nice because it's a little bit easy. It offers its own challenges, of course, they all do. One including that we had to have a blast plate here so that when this came in, we didn't break our aerogel sample. But we can monitor the pressure change, which is a lot easier than measuring these really low flow rates. And so what you get is a curve that looks like this, what's happening. So this is pressure, the pressure we measure in that tank, and this is time. And so initially, this is our tank. We have our aerogel in the tank, and everything's been evacuated, so there's nothing there. We open the valve, and the pressure rises, right, from vacuum, because it's evacuated, up to some some number approaching what we pressurize it at, because the tank fills up with the nitrogen. But initially, none of it has diffused into the aerogel sample. But then, so we open this and then we shut it. And then eventually, you see the pressure drops as the gas diffuses into the aerogel itself. So this is a typical pressure versus time curve that you see in a setup like this. And so you can solve the differential equations that describe that diffusion into the material. We've been doing we do a 2D solution with this because we have a radial direction and an axial direction. But what we really want to do is 1D, so we're trying to make some aerogel spheres. But we can make, basically you can fit the theoretical solution given a certain value of permeability, in this case, that fits this curve, and from that determine the permeability. We've made a few measurements on some things, but this is from that original stump paper for a more dense silica aerogel than the one I just showed you. They think they're seeing this diffusive flow behavior at the low. This is a little more linear. So here, this is in their data, they're plotting diffusivity, which would have been K, and the other thing, again, they mix all these units. But anyways, it doesn't matter which one it is because they both behave the same. It's just a matter of the sample. But they see at the lower number, at the lower values, they do see sort of what they think is the diffusive flow. And this is diffusivity versus density with helium, nitrogen, air, and a fluorocarbon. And so to prove that, they've also gone over here and plotted this diffusivity versus 1 over the square root of the molecular weight of the gas. And in fact, they can see that it does only for this, it only works down here, these values. And so in fact, they see that 1/2 behavior, the 1 over the square root of the molecular weight to show that. So these are sort of 2 studies. This was not, this gas is allowed to diffuse in. It's not like a flow through with a forced flow per se, but it is some interesting work that's been going on trying to understand what's going on, how gas is transported in this material. And so we're doing some work with that. Again, trying different materials and different aerogels to see what we get for that. Okay, the last thing I want to talk about is just a little bit on, oops, sorry. Okay. I want to talk a little bit about another thing you can do is model flow through an aerogel. And all of this is geared towards understanding the flow field, like how does a gas permeate through an aerogel? What is it a function of? How effective can it be? It's of interest to us because both sensing and pollution cleanup applications, catalysis applications. So again, the way to do that is something called the Lattice-Boltzmann method. And it is a non-continuum computational model to model fluid flow. And so you have to discretize or break into parts space, time, and velocities in a lattice. And so we actually analyze you're sort of analyzing every molecule of the flow. And the idea is this is a D2, 2D, 9 position lattice. And the idea is I have a particle at the center, and there is a distribution function that says that particle will either go to any one of these 1, 2, 3, 4, 5, 6, 7, 8, or stay spaces. They call it 9 lattice. But so there's we can say there's a 10% chance it will go here, 20% chance it will go here, etc. So it's sort of a distribution function that models the fluid flow over the lattice. And so it is used in these sort of non-continuum flows. It can also model continuous flow too, but it's applicable, I think, for flow through the aerogel. And so you model at each point in your flow, you calculate the probability of where a fluid particle is going to go. And sometimes it goes this direction and maybe it hits a solid structure. And so you have a bounce back condition. So part of it involves streaming, which is moving the particles forward, and collision, which is when it hits something and it can bounce back. So we've been using it to model flow through porous media. And this is an example of, I just like this image, but this is not necessarily an aerogel. This is simply a porous media where we randomly assign solid and open areas in a structure. And then you can run Lattice-Boltzmann, and it shows you. So what this is showing you is velocities through that porous structure, right? As it makes its way through, it's just repeating each time. But as it makes its way through, and it has to find its way through this tortuous path. And in some cases, it hits a dead end, right? So it has to find its way through the structure. And so that's kind of the first thing we've done, but this has no relationship at all to a aerogel. We just made a random structure. So the next thing to do is to, yes?
What kind of software?
This is MATLAB. So this was done in MATLAB, but the work we're doing now is in, I have a student who is he's a mechanical engineer, but he also studies computer science. He's using C++. So MATLAB is great, but if you have a lot of calculations, a compiled C++ is better. But this was nice in MATLAB. We like that. So the next step is to actually build a model of an aerogel. Again, this is just a porous media. All we did is assign a certain porosity to it. So with the aerogel structure, a lot of people have done work to show that you get a sort of a fractal structure in an aerogel if you do small angle scattering of X-rays. So it can be considered a fractal network. And there's a method called DLCA, diffusion limited cluster aggregation method, to create fractal structures. So what we're working on now is this DLCA, diffusion limited cluster aggregation method, which is actually, the sol gel method is actually, the way that aerogels are formed is sort of like the DLCA method. So in DLCA, particles undergo random walks on a lattice until they collide. So they're just walking around and they collide and they attach. And so this is some work from another group where they've assigned different densities, and this is sort of what they see when they try to create an aerogel structure. And so you can control the density of your structure. And in some ways, this looks, if you remember, I showed you a TEM or tunneling electron microscope image. Kind of looks like that. So you can control the density to build that. So we've been working on doing that, developing this to make our aerogels, but there are two things we're looking at. It's density and pore size distribution. So we need to, and this is in C++. This is in C++. So here's a method of the DLCA method, an image where you have just a single particle, and then you randomly bring in particles from other places, and they move around until they attach, and they build a structure. The one on this side is where we had 3 seeds, and then particles are coming in from the side, they move around until you build a structure. And so we've now built the structure, and what we're doing with this is, at this point, this is still just 2-dimensional. So 3D will take a lot more computational power. But what we want to do with this is build these structures. This is completely random right now. We can build a structure, we can figure out the density, but we want to build a structure that has a pore distribution that matches what we see in our aerogels. So that's where we're going with that. So again, the next step on this is combine the DLCA aerogel structure with lattice-Boltzmann flow to try to better understand flow through aerogels and the properties. We want to try to match this to some of the experimental data. Okay, so that's all I have to say about flow through, and I'm sort of done at this point talking about properties. I spent sort of 3 lectures on properties, and I bring this slide back up that I showed you at the beginning. Again, we've talked about, how do we understand what the porosity is? How do we get density? We did that. Porosity, pore diameters. We didn't talk a lot about measuring particle diameter. That's that Sachs method. But we talked about measuring how do we get that specific surface area. We talked a bit about strength. We didn't talk, actually, surprisingly, I don't know why this table does not have thermal conductivity. Anyway, so we also talk about thermal conductivity, and this is from a reference on drying silicate aerogels, which is good, but thermal conductivity, and now we talk a little bit about flow through aerogels. We have definitive stuff on thermal conductivity. We can measure. We don't have definitive stuff really on flow through aerogels yet. We have some studies trying to measure this conductance or this diffusivity, but not a lot of it. So what I'm going to do, so the last 3 lectures will be more focused on specific applications of all the, we have these great properties, what are we going to do with them? And so the last 3 are on Friday is aerogel windows and some of the things we've done to improve the aesthetics. And then